Clearance is another pharmacokinetic parameter that is essential for us to understand how a drug moves through the body. We measure the drug's capacity to remove drug with clearance. That is, the greater its value, the higher the body's capacity to remove a drug, which means that this parameter is related to the processes of metabolism and excretion. We can understand the concept of clearance in two ways. First, we can say that the value of clearance is the volume of blood that is totally cleared of drug per unit time. This concept helps us to understand how a drug is removed from the body overall. It also helps us to understand the concept of plasma half-life, which we will discuss in the next module. Another way we can understand the concept of clearance is as a measure of the efficiency of an organ to remove drug from the blood. This is more helpful when we want to look at the contribution of different organs of elimination to the removal of drug from the body. It also helps us to explain the concepts of enzyme induction and inhibition and first-pass metabolism, as we will see later in this course. So let's first take a look at clearance as the volume of blood that is totally cleared of drug per unit time. The units for this parameter is typically volume per unit time. And in veterinary medicine, we once again normalize this to body weight so that we can more easily compare values across a wide range of breeds and species. We can conceptualize the body as a beaker of fluid, like the one on the right-hand side of this slide, and clearance as a smaller beaker which we use to scoop out some of the fluid at set periods of time. If we do this, we see that scooping out a fixed volume of fluid with drug in it and replacing it with clean fluid slowly decreases the amount of drug in the body and therefore the drug concentration over time. Looking more closely, we see that the concentration of the drug in the beaker on the left, which represents clearance, is proportional to the concentration of the drug in the beaker on the right, which represents the body. This means that if the concentration of the drug in the body is low, the amount of drug that is removed from the body per unit time is small, even though the clearance, represented by the volume of the beaker on the left, remains constant. Now, let's look at clearance as the capacity of an organ of elimination to remove drug from the blood. We are also dealing with units of volume per unit time here. But in this case, we focus on a specific organ of elimination, like the kidney or the liver. We consider the blood flow to this organ, represented by the letter Q, and the concentration of the drug in the blood as it flows into the organ, C in. We then look at the concentration of the drug in the blood as it leaves the organ, C out. And the difference between these concentrations can be attributed to the processes of elimination. Within this framework, we can quantify clearance as the product of an organ's blood flow and the difference in drug concentration between the blood entering and leaving the organ relative to the concentration in the blood entering the organ. We can call the second term the extraction ratio of the drug across an organ, E, which simplifies the equation to Q times E. Now, if we examine the value of the extraction ratio, we can see that if the organ removes most of the drug that passes through it, the value of E will be close to 1, and we categorize the drug as having a high extraction ratio across that organ. Drugs with extraction ratios between 0.3 and 0.7 are classified as being intermediate, whereas an extraction ratio of less than 0.3 is considered low. And we can bring extraction ratio and organ blood flow together. Then we see that only if a drug passes through an organ with a high blood flow, for which the extraction ratio for that drug is high, will the drug have a high clearance. It is not by coincidence that those organs that play an important role in drug metabolism and excretion, the liver and kidney, are also highly perfused organs with a high blood flow. Finally, we need to point out that clearance is additive. This means that the total body clearance we measure based on how drug concentrations change over time in the plasma is a reflection of the sum of the contributions of all the different organs in the body that play a role in removing the drug from the blood.